Okay, so the first thing here is this one's hard. All right, it looks that way because this one goes down. Every other one we've worked with went up. Doesn't change a thing. Okay, we still do this exactly the same way. The slope on this graph, M, just happens to be negative, which is why its line is going downwards. Okay, why it's descending. Okay, so what we're seeing here, okay, is the Disney Star Wars viewership. That's me taking a shot at Disney Star Wars. It's declining. They don't like what they see. Okay, so what we got here on this graph is the number of viewers in millions, okay, and on the x-axis, time in years. All right, so they're asking what's the rate of decline in viewership. So what they're looking for is how many million viewers do they lose every year. All right, what part of the equation tells me that? The slope. Okay, this is one of the skills that we have to develop, okay, as in physics, okay, is the ability to read graphs, okay, and interpret graphs. We can't just memorize, well, the slope on this graph represents this, and the slope on this graph represents this. If you continue in physics, by the time you get to physics 30, you will have to memorize like 4 dozen different types of graphs, okay, and you're not going to memorize what the slope of all 48 of those are, okay, it's ridiculous. So what you want to be able to do is analyze a graph. Okay? How do I know that the slope of this line represents the rate at which viewers are leaving this? Okay? Is I look at the graph and I say, okay, on the y-axis is the number of viewers, and on the x-axis is time. So this graph is showing me what's happening to viewership as a function of time. Okay? That means the slope will tell me viewers per time interval. In this case, it's years, not seconds. Okay? But that's what it tells me. So I know that if somebody calculates the slope on this graph, okay, what they're going to end up with is viewers per year. Okay? Follow what I did there with the slope? Okay? So slope can represent anything. It just depends what's on the graph. Right? I could have a graph of plant growth that I would measure in like kilograms per decade. I don't know. And then my slope would be, okay, kilograms per decade that the plant would gain, okay, or something like that. But I have to look at the graph and go, all right, on this axis, on the y-axis is one thing, and on the x-axis is another thing, all right? In fact, like we could have this and it could be like the Biggest Loser graph. Okay, where people are like trying to lose weight. Okay, and we'd have weight here on the y-axis, and we'd have time on the x-axis, and it would tell us how many kilograms per week they lose. Okay, that would be the slope. Okay, whatever's on the y over whatever's on the x, that's what the slope will tell us. Does that make sense? So in this case, what we're looking at is the decline in viewership in millions of viewers per year. So according to this graph, Disney Star Wars loses 3.17 million viewers every year. Okay, now, they came out with The Mandalorian last year, so this is starting to go back up. But, okay, yeah, we'll add that on later. Okay, all right, does that make sense to everybody? Okay, number 2, how many viewers will there be 2 years from now? Okay, so we're saying that this is now, okay, the end of the graph will be now. Okay, how many viewers will there be? Okay, well, what's the years going to be then? 17. All right, so 17 is going to be my which value, y or x? X. Okay, so I'm looking for y, okay, because they're looking for how many viewers there will be. So y equals negative 3.17 times 17 plus 63.7. Okay, 63.7 million, mind you, but we're just going to put 63.7 in there. That's where the graph started. So in this case, B is actually way up here. All right? So if I punch that into my calculator, the negative is important. Okay, 3.17 times 17 plus 63.7. All right, so according to that, in 2 more years, the viewership will be 9.81 million viewers. Okay? This is the kind of statistical analysis a broadcasting company would want to know. They need to know how many viewers are we gaining or losing, okay? Like people that want to advertise on their channel would want to know this information. If they're seeing a decline in viewership, they're going, I can find somewhere better to advertise my stuff. Okay, so this is the type of statistical analysis that graphs are used for. Okay, when will the viewership be 0? All right, when means I'm solving for what? Time. Okay, so I'm looking for an x, and what y value am I going to use? 0. Yeah, okay, so y is going to be 0, and I'm solving for x. Okay, so I've got y equals m times x plus b, and I've got to solve for x. So I'm going to go y minus b divided by m equals x. We just said y will be 0, okay, minus b, which was 63.7 million, okay, divided by negative 3.17. And again, the negative is important here, because if I don't put the negative there, it's going to tell me that it'll be 0 back in time. Right? Time can't be a negative number. Okay, so 0 minus 63.7 is obviously negative 63.7. Okay, now if I divide that by negative 3.17, I get that Disney will have 0 viewers in 20.1 years. Everybody all right with that? It shouldn't be. That'll be the end of Disney. Well, but also be the end of Marvel and Star Wars and everything else Disney owns. So keep that in mind. The House of Mouse has a lot of clout. Okay? They have a lot of things. All right. Is that making sense to everybody, how the graphing stuff works? Okay? And I wanted to throw this one at you because we hadn't done one that had a negative slope. Okay? But as you can see, it doesn't change mathematically what we do. Okay, we're still solving for the same thing. We still manipulate the equation in the same way. Okay, all of that stays the same. All right, questions on that? Then we are going to look at the graphs that we're going to have to use in this unit. We're only going to have to look at 2 graphs. Okay, position versus time graphs and velocity versus time graphs are the only 2 graphs that we really worry about in Science 10. So what we got to get out of today, you can find this in your notes package, okay? We need to understand what information can be read from these 2 graphs, okay? Understand how the equations that we use are actually derived from these graphs, and that they basically, these graphs show the same information in different ways. Okay, so as I was saying there before, being able to read and interpret a graph is a really, really important skill that we need to develop in physics. And that's what we're going to look at a bit today, looking at a position versus time graph and being able to go, all right, I just looked at this graph and here's what it says. Okay? Whether we need to calculate anything or not, that's a skill we want to be able to have. Okay? All right, so a position versus time graph, okay, represents or shows us visually where an object is, its position, at various points in time. So as a function of time. Okay? The shape of those graphs can tell us about the movement of the object. Okay? Obviously, we can read the position of the object right off of the graph. That's what the graph is showing us. Where was the object here? Where was the object at this time? Where was the object at this time? Okay? But there are other things it can show us. Okay, not so much from reading it, but from recognizing what different shapes mean. Okay, so with this first graph here, okay, between 0 seconds and 1 second, okay, remembering that this graph is showing us where the object is as a function of time. Between 1 second, or between 0 seconds and 1 second, what does the object do? Nothing. Yeah. It's not moving between 0 and 1 second because its position stays the same. It doesn't change. Okay? At time 0 seconds, the object was at position 20 meters. And at 1 second, it's still at position 20 meters. Right? So it obviously didn't move during that second. Right? That's something that we can just interpret from the graph. Right? Now, between 1 second and 3 seconds. What's the object doing? Yep, moving 40 meters, okay? Moving 40 meters forward or backward? Forwards. How do I know that? Yeah, the change in position is positive, yeah, or up, okay? So it's going from position of 20 meters to a position of 60 meters. All right, there's one more thing we can interpret from that. Okay, we do know it's moving. We do know it moved 40 meters in 2 seconds. Okay. Did it do that at a constant velocity or did it accelerate? It did it at a constant velocity. Okay. A lot of people want, like, gut reaction. They look at that line, see it going up, and they want to say accelerate. Okay, because they see something increasing, and acceleration is an increase in speed. Okay, that's what they think. But here, we actually don't increase our speed. Our speed, our velocity, remains the same here. In the first second, the object goes 20 meters. In the second second, the object goes 20 meters. So it covered the same amount of distance every second. That means it's traveling at a constant velocity, in this case of 20 meters per second. Okay? So even though our gut reaction is to say, oh, it was accelerating, okay, we have to look at that graph and go, oh, actually it's not. It's not accelerating here because it's covering the same amount of, or changing its position by the same amount every time interval, in this case every second. Okay? So it was traveling at a constant velocity of positive 20 meters per second. All right, so if I put this graph on a unit exam or a quiz, and I ask you exactly that, okay? There's a lot of different point values for that question, okay? What we just said, moving at a constant velocity of positive 20 meters per second or 20 meters per second forwards is 5-mark answer, okay? But when we were building up to that, okay, we were like, it's moving, okay, that's 1 mark, okay? It's moving forwards, okay, that's 2 marks, okay? It's moving forwards at a constant velocity, that's 3 marks, okay, and so on. So you're getting, like, there's certain levels of detail in that answer, okay? Be as detailed as possible when I'm asking you, interpret the graph.
So whenever, like, a line is going up, it's always moving forward, and then when it's going down, it's moving backward?
On a position time graph, yes. Okay, I don't want to say that on every graph because the one we were looking at there that was the viewership, it's not about moving, it's about how many people are watching, right? Anytime the line is going up, there's a positive change in y, in whatever's on the y-axis. That's the general answer that applies to all graphs. Does that make sense? All right, what's the object doing between 3 and 4.5 seconds? It stops, right. Its position doesn't change. It stays at position 60 meters for 1.5 seconds. What is it doing between 4.5 and 6 seconds? Moving backwards 40 meters at a constant velocity, right? Okay, there's that level of detail, right? It's moving backwards, yes. How is it moving backwards? At a constant velocity. How do I know that? Well, every time interval, it moves the same amount. Okay, now we only had 1.5 seconds here, okay, but that's what it's doing, okay? If it's a straight line, the rate of change is constant. Okay? All right, that's the stuff we can interpret from the graph, okay? Now there's some things that we might be able to calculate from this graph. Looking at this graph, what is the total displacement of the object over the whole trip? 0. Okay, how do we know that? Yeah, it goes back to its starting position. Remember that displacement is final position minus initial position. My final position is positive 20 meters. My initial position is positive 20 meters. 20 minus 20 is 0. Didn't go anywhere. Okay, now, would I actually have to show that calculation on a test? No, that would be a 1-mark question. Okay, now, on that note, the point value for a question is always an indicator of how much work needs to be done for that question. Okay, This happens all the time. I have a 1 mark question like that, and people show me 5 marks worth of work that's all wrong. Okay? That's a recognition thing. If it's out of 1 mark, the answer is right in front of you and requires no work. Okay? Don't show me 5 marks worth of work for a 1 mark question you definitely did it wrong. Okay? Or you wasted a ton of time to prove something that was worth 1 mark. All right. What's the average velocity of this object over the whole trip? Should have been that fast. Woo. I'm too old for that. Okay. Sorry, my heart rate down. Mr. Real did that to me yesterday too. He threw something on the table in the prep room and it smacked down really loud. And okay. Velocity is total displacement divided by total time. What did you just tell me the total displacement was?
0.
Then what's the average velocity? Right. That's why that should have been right away. Yeah? Okay. Velocity is total displacement over total time. Total displacement is 0. Velocity is 0. Didn't go anywhere. That's that whole we walked like Home Depot question that we did the first day. Okay. All right. What's the total distance traveled by this object?
60 meters. Oh, I mean like that's how high it goes.
Okay. So is distance scalar or vector? Scalar. So it doesn't care that it goes forward and backward, just how far? Okay. How far does it go here? 0. How far does it go here? 40. How far does it go here?
0.
How far does it go here?
40.
How far did it go?
80.
Right. Hey, that's not so tough, is it? Okay. 80 meters. Went 40 meters in that one part, 40 meters in the other part, and 2 parts where it didn't go anywhere. Okay. Total distance traveled, 80 meters. What's the average speed of this object over the whole trip? That one I don't expect you to get right away, because you actually have to punch something into your calculator for that one. How do we calculate speed? Distance over time. All right, we just figured that out. How long does this whole trip take? 6 seconds. Okay, so 80 over 6 is what? 13.3. 13.3 meters per second. Okay? That's the kind of thing I'm going to ask you to do with a position versus time graph. Okay? Because that's really about all we can calculate from a position versus time graph. Okay? We can interpret the type of motion that's going on. We can determine what displacement is. We can determine what distance is. We can determine velocity and speed off of these graphs and that graph. Okay? That's what we can do. Now, I don't expect that you memorize that. Right? This is I need to look at my graph and interpret this. I can figure this out because I know V equals D over T, okay, that kind of thing. Right? Everybody okay with that idea? What's the object doing in that second graph? It's accelerating. Okay? This is what acceleration looks like on a position versus time graph. Okay? When you accelerate, you go faster and faster. If you go faster and faster in each equal time interval, you will also go further. Okay? If I'm increasing my speed, then in the first time interval, I'm going to go like this far. Okay? I'm sorry, I'm using my color here. So between 0 and 1 seconds, the object only goes that far. But between 1 and 2 seconds, it goes that far. And between 2 and 3 seconds, it goes that far. And between 3 and 4 seconds, that far. And then even further. Okay? Because as it goes faster, it obviously travels further. Okay? Not just further in total, obviously that too, but further than the second before. Okay? And so what that ends up looking like on a graph is a curve. Okay, so it curves upwards. Okay. What would a decelerating object look like? Right, it would curve. Okay, but is it going to curve like this? Like I saw a bunch of people do this. Is that a decelerating object? No, that object's speeding up backwards. Okay? Deceleration on a position versus time graph, how's that going to work? Still curved. Okay, so I see people doing this. Yep, that's actually decelerating in reverse. Okay, what was the object doing right here? Not moving. So if you're slowing down, your line should get flatter. Okay, flatter and flatter. So this is a decelerating object. It's the opposite of this curve, right? Between 0 and 1 second, it went that far, okay? And then between 1 and 2 seconds, it went this far, and then each one, it gets shorter and shorter, right? It's slowing down. Everybody with me there? Okay, it gets flatter and flatter, because once the line's flat, the object's not moving anymore, okay? These are the interpretation kind of things that come up in certain types of questions. All right. Now, slope calculations. We've already talked about this a little bit, but I want to just quickly review it. Okay? We use the graphing equation to calculate slope. What part of that equation is slope again? M. Okay. So when we want to calculate M, we subtract B and divide X, and we end up with this. Okay? Which is the same as this, rise over run. Now, as I told you yesterday, the slope of a line on this type of graph is equal to the velocity of the object. Because when I calculate the slope, I'm taking displacement, the change in y, and dividing it by time, the change in x. Okay, so the rise is change in position or displacement, the run is the change in time, right? So when I calculate the slope of a position versus time graph, I'm calculating the velocity of the object, right? Again, not something you need to memorize, something you need to get from your analysis of the graph, okay? The way we arrived at that is we manipulated for slope, and then we looked at what are we putting in this formula. On the y-axis are positions. On the x-axis are times. Oh, well, that calculates displacement over time. Oh, so it calculates velocity. You can do that with any graph. We did that with the viewership graph. Okay? We figured out that the slope represented the decline in viewership because it was millions of viewers per year. Okay? So slope is going to represent something different on every graph, and it isn't hard to figure out what it is. You just have to set it up and look at what are you plugging into the formula. Okay? What does that calculate when you plug it in? Okay? In this case, it calculates displacement and time, so that's velocity. Questions? No? No. Okay, so this is a position versus time graph. What's the object doing in part A? Moving forwards. Constant velocity. Okay, 6 meters per 2 seconds is 3 meters per second. Okay, good. So there's that's the change, right? That's the difference in the marks. It's moving forwards. It's moving forwards at constant velocity. 3 meters per second. Okay, what's it doing in part B? Nothing, right? Okay, what's it doing in part C?
It's going backwards.
At constant velocity. We won't calculate it right now. We'll calculate it later. Okay, what's it doing in D?
Not moving.
Okay, E?
Moving forward.
Moving forwards. Constant velocity. F?
Moving forward.
Okay. Where is it going faster, E or F? Okay, how do we know that?
It's going up.
Right, it's steeper. And what does the steepness or slope of the line represent on this graph?
Height.
velocity, right? We just figured that out, right? We were just talking about how if we go y minus b over x on this graph, that's displacement over time, which is velocity. So the slope of the line represents how fast it's going. So the steeper the line, the faster it's going. Okay? So you guys, like, without even thinking of this, you intuitively recognize that E is bigger than F because it was steeper. Okay? But we also have to recognize that on this graph, steepness or slope represents velocity. All right, a couple calculations I want you to do from this graph. I want you to calculate the total displacement over the entire trip. You should be done already. Right. Okay, between 0 and 18 seconds, it comes back to 0, right? Okay, that one was easy. Now, calculate the total distance traveled. I'll give you a couple minutes on that one. So in order to get the total distance traveled, I need to figure out how far the object goes in all the parts of the trip where it's actually moving. Okay? So in this first part, part A, it goes from a position of 0 to a position of positive 6. How far did it go? 6 meters. Okay, how far did it go in part B?
0.
Right? Okay, and then in part C, it goes from 6 to negative 10. So that's 16 meters. How far did it go in D?
0.
Right? And then between D and the end of F, it goes from negative 10 back to 0, so it goes 10. I don't have to figure that out one piece at a time. I can just figure that out all together. Okay? You could do it one piece at a time, too. It doesn't really matter. All right, so that means that we went 2632 meters. Okay. All right. Trip takes 18 seconds. What's the average speed?
Is it
2 meters a second.
Nope, it'll be a little less than 2. Because 32 over 18 is like 1.77, 1.8 meters per second. Okay, because that's going to be total distance over total time, 32 over 18. Okay. All right. Is that making sense on that?
If it was on the test, like, we would round it to 18, like, we wouldn't say 17 or something.
No, that's why I said the trip takes 18 seconds. Okay. So I would say that in the question. So there's some little part here where it's flat.
Oh.
Because it's a little bit past where 17 would be. Like 17 would be about there. So that's why I would say it's 18. Okay. Everybody okay with the position versus time graph so far? All right, so on this graph here, okay, what is this object doing?
Accelerating.
It's accelerating and it's decelerating and and there's actually a lot of things going on in this graph. Okay, during this first part, okay, between 0 and probably about here, okay, the object is actually accelerating and going faster because we have a curve that's getting steeper and steeper. Okay, everyone follow me what I mean by steeper and steeper there? Yeah. Okay. After this point, okay, so after right here, the line starts to flatten, right? Okay, it's decelerating there, right? And then right after it gets to here, what does the object start to do? Right, it starts to accelerate backwards, okay, until it gets to about here. And then what does it start to do? Well, it looks to me like the line is getting flatter and flatter because it's decelerating. It's slowing down again. Okay. Now we've been using the term decelerate. I just want to warn you that in physics that word doesn't exist. Okay. Acceleration is any change in velocity. There's positive acceleration and negative acceleration. Okay. There's no such thing as deceleration in physics. Okay. The true definition of acceleration is any change in velocity. Deceleration is a layman's term. Okay. All right. So what is this a graph of? a graph of someone throwing something up in the air. Okay? During this part of the graph is the part where they're actually accelerating the object and throwing it upwards. Okay, so it's still in contact with their hand and going faster and faster. As soon as it leaves their hand, what does it start to do? Right, gravity starts to pull it back to Earth. Okay, and so it starts to slow down, slow down, slow down. Then, right there at B, how fast is it going? Right there at B. It's not, okay? Remember, we said the slope of the line on this graph is velocity, right? Well, whoop, still the mark on my head. Okay, the slope of the line right there at B is 0, it's flat. Okay, and then notice that on one side of B and on the other side of B, the line is, like the shape's the same, right? It's a mirror image. So this is where the object is slowing down due to gravity. This is where the object is speeding up due to gravity. The acceleration is the same, okay? It's 9.81 meters per second squared. That's how acceleration works. Okay, due to gravity, it's always 9.81. Right? So on the way up, it's accelerating downwards at 9.81 meters per second until it stops. And then it accelerates at 9.81 meters per second squared, except it actually starts to move downwards. Okay? And then part C is where the object is caught and slowed to a stop. Okay? Would I ever ask you a question like that on a test? No. Okay? I would never say, here's a graph. What's happening? Now, I might say what's happening in terms of you tell me it's accelerating here and decelerating there. Okay? That part, yes. Would I actually ask you, what is this? No. There's not really a way for you to know that. Okay? Wouldn't really be a fair question. I can ask you to interpret the graph, but beyond that, I can't say, is this person, there's no way you would know that's a graph of a person throwing something in the air. Okay? That wouldn't be a fair question. All right, so on this graph, we just said that at point B, the object's not moving. How long is it not moving for? Not even a second. It's an instant. Okay? It's instantaneous velocity at the top of its flight is 0. Okay? It's slowing down, slowing down, slowing down, and at the very top of its flight, for one instant, its velocity is 0. And then it begins to actually move back downwards. All right? So, one of the things we sometimes look at, you won't be asked to calculate this, but what we look at is instantaneous velocity from a position versus time graph. Okay? Normally we just calculate velocity on a position time graph by going displacement over time. But when we have a graph where acceleration is happening, we don't have a straight line. Okay? So we can't calculate it in the same way. So sometimes a question might ask us something like, what is the instantaneous velocity at this particular time? Okay? So let's say they asked us, what's the instantaneous velocity at this point right here? Okay? I can't just go distance over time, or displacement over time, because I don't know what the displacement is. Okay? I know what the displacement is to this point, but if I calculate d over t with this point, I'm calculating the average velocity between here and there, which is not how fast it's going at this point. It's how fast it was going on average between here and there. So, to calculate instantaneous velocity, we need to draw what's called a tangent. How many people have heard of that? Okay. So a tangent is a line that touches a curve at any point, but doesn't cross it. Okay. Now, I'm about to explain to you the only thing that I ever understood in university calculus. Okay? It was the first day. Okay? I passed the course, but I only understood the first day. Okay? It's very scary. So, to a mathematician, a curve is an infinitely large number of infinitely small straight lines whose slope changes at a constant rate. Okay? So when a mathematician sees a curve like this, they see it in the same way you see a low resolution video on YouTube. What can you see in a low resolution video? You can see the pixels. Okay? So a computer, when it makes curves, can't actually make curves. it has to use the pixels on and off. That's the only thing that a computer can speak is binary, on and off. Okay, so what it does is it makes the pixels really, really small, right? So if you're looking at something in 4K, okay, it's 3,840 pixels on one, and it's 2,800 and something on the other, right? So it's a lot of pixels, okay, and they're all very, very small, okay? If it's low resolution, then it might only be like 800 by 640. And then the pixels are bigger, and you might be able to see them, right? So when a mathematician looks at a curve, they actually see all the little lines that are strung together. Now, each one of those little lines would have a slope. Agreed? So if I draw a tangent that touches the curve right here, it'll be parallel to the curve because it doesn't cross it, which means it has the same slope as the curve at that point. And then I can cheat. Okay? And I can take my tangent line, like I did right here, and I can make it long enough to do a slope calculation. I could get b, I can get y and x, okay, and I can calculate m. As long as I draw a tangent that touches the curve so it's parallel to the curve. Okay? Now, you're not going to be asked to do that. Right? Okay? The reason you're not going to be, there's a couple of reasons. First off, we make all of our graphs digitally, so you're not going to be drawing on them. Okay? And secondly, if I ask you to do that, all 26 of you, okay, I will get 26 different answers. They'll all be in a narrow range, they'll all be close, but they'll all be slightly different because everybody's going to put their ruler on that curve in a slightly different way. Okay? And it's going to look like a tangent to you and to the next person and to the person after that, but they're all going to be a little bit different. Okay? So then I have to be the guy that goes, all right, I'm going to accept as the right answer any numbers between these two numbers. And if you're just outside of that, I have to go too bad for you. Okay? So we don't do that. Okay. Making sense? You're not going to be asked to do that, but it's just so you understand that on a curve, there's a lot of little instantaneous slopes. Okay? Now, before we get to that, I think we'll actually leave it there. Where are my position time graphs? There. Okay. So let's have you guys try this one. I want you to calculate total displacement, total distance, average velocity, and average speed. The answers are there in bold, so you can check them as you go. Okay? But using this graph, I want you to calculate those things. All right, so on this one here, okay, total displacement, final position minus initial position. Okay, so on this graph, that's 0.5 minus 0.2, 0.3 meters, and that's positive. Okay, because it did finish in front of where it started. Okay, and then for total distance, well, we got to do what we did on that other graph. Okay, in this one here, we go from 0.2 to 1, so that's 0.8, and then here we go 0.5, so 1.3 meters total distance. Okay, and then the other ones, okay, just v equals d over t. So tomorrow, we'll be looking at velocity versus time graphs, okay, and then on Monday, we're going to be doing our lab on position versus time graphs. Okay, so that's where we're headed here over the next couple of days.